Welcome back to Larry's Classroom. Today we're going to begin a discussion of series circuits. We've got a simple circuit like this, a voltage source, and a couple of resistors. Now the battery will create the negative charge, which will repel the electrons and make them travel this way through the circuit. And this will put charges, if you were to measure the potential difference across the resistors, you will see a negative charge here, a positive charge here, or polarity, excuse me, negative here, positive here. What you will notice here, this is a electron flow, and it's traveling counterclockwise through this series circuit, or we could call it a loop. You will notice that inside the voltage source, the electrons travel from the positive to negative. But outside the source, in the loads or the power consumers, that the electrons travel from the negative to the positive, the negative to the positive. The battery, this here difference in charge, causes electron drift that gets this current flowing through the circuit. We're going to draw a little bit more complicated circuit here. We're going to have 3 resistors in this one. We're going to label these R1, R2, and R3. Now we're going to assume a current flowing here of 2 amps. Which will go that will occur everywhere in this circuit. So we'll have the 2 amps flowing through this voltage source, the battery, inside the battery, plus to minus. We'll have the 2 amps here flowing through the R1, and inside of R1 it'll be going from minus to plus. This is a source, this is a load. The load, the current electron flow goes from negative to positive. Inside the source, it goes from positive to negative. Again, we have 2 amps here flowing in this direction, and 2 amps flowing this way on this one. The potential difference across this battery provides the motivation to cause these electrons to flow through this circuit. And we'll make these little ovals here to kind of represent the electrons, negative charge and an arrow in the direction. We'll do some more here, negative charge and an arrow. Now you can notice these electrons are traveling in the same direction all the way around this loop or series circuit. And that is because of the potential difference created by the battery is causing electrons to be repelled from the negative supply, and it's being attracted by the positive charge. So here inside the battery, the chemical action is causing the electrons to go towards the negative terminal of the battery, which is leading to a surplus electrons there on the negative terminal and a deficiency of electrons on the positive terminal, creating the charge and the potential difference across the battery. Same polarity throughout the circuit shows up. Same things happen here. The negative charge, this end of the battery is closer to the negative terminal, this one's closer to the positive terminal, so we have a potential difference across here, causing electrons to travel in the clockwise direction in this particular drawing. Same thing here, this end of this resistor R2 is closer to the negative terminal, this end's closer to the positive terminal battery. Same thing happening, it's causing electrons to be, the electron drift to occur in that direction. So this is happening in all of the components in this circuit. Basically, as an electron leaves the battery, it causes electrons all along the circuit to be repelled in that direction, in the counterclockwise direction, which will cause an electron to enter the positive terminal battery at the same time. And we see an electron going into the negative terminal of R1, same time an electron coming out of the positive terminal of R1. Same thing happening in R2, same thing happening in R3. So this circuit, we end up with the same current flowing everywhere in the circuit. In a series loop, a series circuit, or a single loop, the current flow is equal everywhere. And another thing we'll notice, I'm going to modify this drawing just a little bit. I'm going to put R1 back here, R2, R3. It really wouldn't matter if we went to R1 and then to R2. The little hops indicates that there's no connection here. And around here to R3 and back to the battery, we still have the same current flowing everywhere in the loop. So as far as the individual resistors, the order of connection really doesn't affect the current in each of them. It can affect other things, but for this particular case, if we have electron flow in this direction, what you will notice here is by changing these connections, I still had a left to right flow of the electrons through R1, I had a top to bottom flow of the electrons through R2, and a right to left flow of electrons through R3. So the impact of changing that didn't really have any impact on how the current flowed through each resistor. I'm going to draw another circuit here. This one's going to start with a single resistor in it. I think I'm going to make this a little smaller so I can put a little more stuff on the board here. We'll call this a 4 ohm resistor. The little omega symbol for ohms. We have 12 volts, negative to positive. We have our current flowing this way. We can calculate this current. We know that I, current, equals voltage divided by resistance. So in this circuit we have 12 volts divided by 4 ohms. So we have 3 amps flowing in this circuit. Now we're going to change this circuit a little bit. We're going to add an additional resistor to it. Same power supply. We're going to have two resistors now. This was R1. Now we're going to have R1 equal to 4 ohms. And now we're going to have here R2 equal to 2 ohms. Now what do we have? We have a total resistance, 4 plus 2, of 6 ohms. We still have 12 volts. So 12 volts divided by 6 ohms gives us, we now have 2 amps. So we've reduced the current flow here, 2 amps, by adding an additional resistor. And still the electron drift that is the current flow is still in the same direction. It's on this resistor, one top to bottom, and this one is top to bottom, and this one's top to bottom. The electron drift is the same everywhere in the circuit. Basically, an electron pops in out of the power supply, causes pushing along, and another one pops in here. The speed of the electrons is not the speed of the current flow. The propagation time, how long it takes for one electron to leave the negative supply and another electron to enter the positive supply, that is the speed of the current flow. And that is not, it's a different electron comes out of here, out of the negative supply, than comes into the positive supply. And what we use here to get the total resistance, we said that R total is equal to R1 plus R2 plus on up to Rn, however many resistors you have. In this case, we only had 2. So we had R total equal to R1 plus R2, which was 4 ohms plus 2 ohms, which was 6 ohms. And that was the number we used up here to calculate our current. The voltage didn't change, but the resistance increased. So if we draw another circuit here, we're going to have a very similar circuit. We're going to put one more resistor in here, which we're going to just call this guy R3, just so we don't have the same labels as we had on the other ones. And we're going to say that is equal to 6 ohms. Here we got the 12 volts. Current equals voltage divided by resistance, which we had 12 volts divided by 6 ohms, and that gave us 2 amps. So what we see here is that when we added the 2 ohms, originally we had 3 amps. We added the additional 2 ohms in this second circuit. That caused the current to go down, more resistance, what gave us less current, 2 amps. We replaced these 2 resistors with an equivalent resistor that was also equal to 6 ohms. Our total current didn't change. We still had 2 amps here. So this kind of is an example of how series resistance adds up, same current through every one. So resistance in series, very simple, adds up just numerically. R total is equal to R1 plus R2 on to however many you have. Could be R3, R4, R10. Our examples, we've only used 2. And when you do this, when you sum the resistors in series up, you get this, which you can use a single resistor to replace that series of resistors for controlling the current flow in the loop. Do a couple more little examples here. let's say we have a little battery here. And we have a resistor here. We'll call this R1 equal to 3 ohms. And we have another resistor R2 equal to 2 ohms. What does RT, our total here? Well, our total, using the formula we're given before, is R1 plus R2 plus R3. Adding up however many resistors we got, we're going to go R1 plus R2 because we only have 2 resistors in this case. So our R total will equal R1, the 3 ohms, plus 2, the 5 ohms, R2, 5 ohms. So basically we have R total equals, I want this to be 2 ohms, excuse me, a 2 ohm resistor. So that our total is 5 ohms. We had a 3 ohm and a 2 ohm. We add them together, we got 5 ohms. Now, if we had 50 volts here, we've got some current here, so we would like to figure out what the current through this loop would be. Well, we come up with a total of 5 ohms. These 2 resistors here are equivalent to a single 5 ohm resistor. So we have current I is equal to voltage divided by resistance, 50 volts that we have here in our power supply, 5 ohms, which is the sum of these 2 resistors, which we calculate over here, and that gives us 10 amps of current flow through this loop. 10 amps. 10A. So we're going to talk a little bit more, and we could replace this with a 5 ohm resistor if we wanted to and get the same result. We just put this thing in here and put the RT, 5 ohms. That gets us back to what we had here, 50 volts divided by 5 ohms, still 10 amps. So as far as controlling the current in a loop, setting the current in a loop or in a series circuit, how many resistors you have doesn't really matter. It's the total resistance of those resistors. And we had this series resistance formula, which you'll probably use more often than you think, and we've done a few examples related to that. We're going to try to do some show how the IR drops add up in a series circuit. So we're going to draw, say, IR drop, of course, is voltage, and we say IR, current times resistance. That gives a voltage, the amount of voltage that appears or drops across the component. This is going to be a 12 volt supply, and we're going to draw 2 different resistors in series. R1, this is going to be an 8 ohm resistor. R2 is going to be a 4 ohm resistor. So we can calculate the current again. The current will be the 12 volts, which is voltage divided by current divided by the total resistance. We use our resistance, series resistance formula to come up with 12 ohms. By 12 ohms gives us 1 amp. So we have 1 amp of current flow I'm just going to use the symbol A, 1 amp of current flow, and it's going again clockwise from the negative terminal of the source to the back to the positive terminal of the source. We're going to label these points. We'll call this point A. This over here we'll also call point A, because the resistance in that wire is essentially 0. We'll call this point B, and we have point C, which is both ends of this wire. Now we're going to calculate the voltage. We've calculated the current through the loop. We found it to be 1 amp. So let's calculate the voltage that appears across this R1, or what we would call the voltage drop across R1. We're going to say that voltage equals current times resistance, which was why we call it IR drop. Our current, we've calculated here using the total resistance and the supply voltage, is 1 amp. And we're going to multiply that, we use the dot here, times the resistance, which is 8 ohms. And we're going to get 8 volts. So 8 volts will appear across this particular 8 volts. And that will appear from here, from this point A to this point B. We'll call this V1, voltage across resistor 1, V1. Now we're going to calculate the voltage across R2. Same formula, voltage equals IR, current times resistance. The same 1 amp, because the current in the loop is the same everywhere. 1 amp. We're going to multiply that times the 4 ohms that we have now. Is a different value of resistance, 4 ohms. And we're going to say that 1 times 4, we have 4 volts. So right here we have 4 volts, which we'll call that V2. So the voltage across V2 is less, but what you will notice is these two voltages, 8 volts plus 4 volts equals 12 volts. And this adds up to the same amount of voltage as the voltage supply. And you'll always find that in a loop. If you measure the voltage across every component in a loop and you add that up, you should get the same voltage that the supply was providing. And we'll kind of do a few more examples on that. We can use that knowledge that the voltages across the voltage drops, resistors, loads, whatever you want to call them, add up to the same voltage as the supplies to determine a few things. And I'm going to give you, we'll call this VT. I'm going to put polarity on it, but it's not really necessary. R1, R2, R3, and the voltage across R1 we will call V1. The voltage across R2 we will call V2. The voltage across R3 we will call V3. So, as we saw in our previous diagram, we found that the voltage total, or the voltage supply, added up to the voltages across the jobs. V1 plus V2 plus V3. And this is very similar to our series resistance formula that we talked about a bit ago. The same thing happens with series voltage. It adds up. And this could be, you know, as many voltage drops you have. There could be 10, there could be 100, there could be 2, but always when you measure all those voltages and you add them up, they should add up to the supply voltage. So we're going to show a little example here, another little example, and we're thinking about how voltages add up. Let's just say that we had, now I'm going to draw a symbol you haven't seen before, which is a symbol for a plug on the end of a electrical cord. Now this one's plugged into a 240 volt supply. And we're going to put 2 light bulbs in series here. And we're going to go back to, so we've got 2 light bulbs. And this is a 120 volt, 100 watt light bulb, another 120 volt, 100 watt light bulb. Now, because these are identical light bulbs and they're designed for the same amount of current, because they're both 100 watts and 120 volts, they should have the same resistance. Let's quickly calculate that. We know that resistance equals voltage over current. So we have here the resistance equals 120 volts. No, I didn't. That's not the correct formula. I want to do resistance equals voltage squared. Excuse me. We're going to use one of our power formulas because we're given power and voltage. Resistance equals, power equals voltage squared divided by power. So for the resistance of these light bulbs, being they're identical, we're going to calculate based on the voltage they're designed to operate on and the power rating, which this is equal to 120 volts squared over 100 watts, which comes out to 144 ohms. So each of these particular resistors or the resistance of the filaments in this light bulb is 144 ohms. And being they're equal resistances, currents equal in a loop everywhere, they're going to end up with equal voltages. And we know that the voltage drops around a loop have to add up to the voltage supply. Well, how can we get 2 equal voltages that add up to 240? You got to get 120 volts on each. 120 volts on each. So that what we've shown here is that 2 identical light bulbs in series could be operated on twice the voltage supply normally used for a single one of those light bulbs. Now this doesn't work out quite so good if they're not identical light bulbs. We're going to change these light bulbs a little bit. We're going to replace this one with a 60 watt light bulb. So now we've got a 120 volt, 60 watts. Now if we use our resistance equal to voltage squared over power, and now we're interested in using the voltage that it's designed to operate on and the power that it's designed to operate on. So we end up with here 120 squared over 60 watts. And we end up with a different value now. We end up with a 240 ohm resistor, or 240 ohm filament resistance. So we can write that here, 240 ohms. The problem is now they're not equal resistances. The voltages are not going to divide up equally. They're still going to have equal current because around a loop our current is always the same. I for current. But they're not going to be equal voltages dropped across each of these. And they're both designed to operate at 120 volts, so you would like that. So let's see what will happen here if we use the the total current to come out what the resistance would be, or the total resistance. Well, we had 240 ohms and 144 ohms, so we have voltage over resistance. We have current equals voltage over resistance. We have 240 volts supplied right here. The 240 and 144 adds up to 388. 240 volts over 388 ohms. When we calculate that out, we end up with 0.625 amps. So we're going to have 0.625 amps flowing through each of these each of these light bulbs. And now let's look at our power formula, and let's figure out how many watts are going to be dissipated for each one of these. So we're interested in, we're going to know the resistance. Okay, we know the resistance, we know the current. So for the 60 watt light bulb, we have, remember, the power equals I squared R. And we have an I of 0.625 amps. And we're going to square that number. And we're going to multiply that times our resistance, which we calculated to be 240 ohms. I'll use a little X this time. 240 ohms. We end up with 94 watts. Well, 94 watts being dissipated by a 60 watt light bulb, we're probably going to burn it out quickly. Now let's do the same thing for the other light bulb, the 100 watt. Power equals I squared R equals the same current. And we'll square that. We're going to multiply that times the now 144 ohms. Let's write that a little neater. 144 ohms. And we end up with 56 watts. Well, the interesting thing you see here is because the resistance of the higher wattage light bulb is lesser, which is needed to get the greater current when it's operating on its normal voltage, we end up with less power dissipated on that particular light bulb also. So when we put them in series with the two different light bulbs, what we see is that the smaller light bulb, the 60 watt, will be brighter than the 100 watt light bulb, which will be dimmer. So we put them in series because of the resistance. This is the way they work to get greater resistance to get the lower wattage light bulb, lesser resistance to get the higher wattage light bulb. We end up with less power dissipated on the higher wattage light bulb and more power dissipated on the lesser wattage light bulb. So when if we put a 60 and 100 in series with 240 volt supply, we would see the 60 watt light bulb, the one light bulb that was designed for 60 watts, to be brighter than the light bulb that was designed to be a 100 watt light bulb. And the reason was because we were putting 94 watts out here and 56 watts here. Now let's do one more thing real quickly. Let's figure out what the voltage would be. We have a 0.625 amps in both of them. In the first light bulb, the 60 watter, again we'll do the 60 watt here. and we'll put the 0.625 amps. We're using the voltage is equal to IR. We've been talking a lot about IR drop. 6.25 amps, and we're going to multiply that times, so we calculate the resistance up here to be 240 ohms. So let's take my calculator and calculate that voltage that's on there. 0.625 times 240. So we'd actually end up with 150 volts here across this 120 watt light bulb, which you can see we're over voltage in it. Why it's brighter, and probably why it will burn out pretty quickly. Now let's do the 100 watt one. And we're going to use the same formula, voltage equals I times R, and we're going to go with 0.625 amps. And we're going to multiply that times the resistance we got here, which was 144. And we end up with 90 volts here. So this 120 watt light bulb, when you put it in series with a 60 watt light bulb, and your supply is twice what the nominal supplies where these light bulbs are, is actually going to only get 90 volts supplied to it, which is why it ends up being dimmer. But you will also notice that 150 plus 90 plus 90 volts is equal to 240 volts. So we still have the proper V total equals V1 plus V2, 150 plus 90. So the voltages add up right, but they don't split right, and we end up basically overdriving the smaller load and underdriving the lesser load. So if you want voltages if you want to run loads in series, they need to be designed for the same current, which they were not. The 60 watt light bulb was meant to have a half of an amp, and we actually ended up with 0.625, which is a little bit more than a half of an amp, and the 100 watt is designed to have 0.83 amps, and we had 6, which was a little less. So the 60 watt light bulb ends up with excess current. The 100 watt light bulb ends up with not enough current. This is why we get the more wattage here and the less wattage here. Why we end up overheating and burning out the 60 watt light bulb probably pretty quickly. Well, what would normally be the brighter bulb runs dimmer. So a series circuit like this, if you want voltage, your loads need to be designed for the same current, because current in a loop is the same everywhere. And in the case of these two light bulbs, they're not designed for the same current, and things don't work out so well. Anyway, I think I'm going to call that good for today. Try not to get this lecture to going too long. Be sure to subscribe so you get notifications, know about the new stuff, and until the next time, keep on learning.